In this video, we're going to show how to calculate moments, centers of mass, and centroids for a plate of constant density. Now, before we start with a plate of constant density, we're going to look at the center of mass of a bar. So center of mass on a bar. So imagine I want to balance a bar. We're going to put a fulcrum at a single point, and the bar should balance left and right. Now, if that bar is a constant weight and constant thickness, then putting the fulcrum at the very center of the bar should center the bar. We're going to assume that, again, there's no wind or any other types of forces affecting the bar other than its weight. Now, what if the bar has weights hanging down from it? Then when you balance the bar, both the weight and the distance from the fulcrum matter. So if I put the fulcrum here, I have to take into account the weights, and I have to take into account how far those weights are from the fulcrum. So what we can do is we can try to find the center of mass of a bar with weights hanging. That is the center of mass in one dimension. So you start by designating an origin someplace on the bar. And then you count the moment about the origin. The moment about the origin is taking into account both the mass and the distance away from the origin. That's what these x1, x2, and x3 are. Those are the distance away in terms of the x value, and the m1, m2, m3, so on, are the masses. Now, because we designated an origin, some of these x values could be positive, some of these x values could be negative. We get an equilibrium if this number is 0. And if we got an equilibrium, then that would mean that the balancing fulcrum being put at the value of 0 would make everything balance. Usually that doesn't happen. And so the center of mass is going to be the place where the fulcrum could be relocated to find the equilibrium. The way we do that, the way we calculate center of mass, is we take the m, the moment. Again, this 0 is basically the moment from 0, and divide it by the mass, the total mass of the thing we're looking at. And it turns out that numerical x value will be where the center of mass is in that x direction. Remember, we're talking about one-dimensional center of mass here, and that means all we're looking at is essentially weights on a number line. So we calculate the moment from 0, and then we divide by the total mass. That will give us where we balance. Let's do an example. Let's assume we have a weightless bar, maybe just a string or something, and it has 4 weights on it. There is a 3-pound weight at the origin. Think of this in the XY plane, although all of the weights are going to be on the x-axis. A 1-pound weight at the point 20, a 4-pound weight at the point 60, and another 4-pound weight at the point 9, 0. Let's find the moment about the origin and then use that to find the center of mass. So our calculations are pretty straightforward. The moment about the origin, since there is a 3-pound weight at the origin has X value of 0. So the origin obviously is the point 0, 0. So we would take the mass, the 3 pounds, and multiply it times the X value of 0. Then I look at the next weight. The next weight is 1 pound, and it is 2 units from the origin. The next weight is 4 pounds, and it is 6 units from the origin. And the next weight is another 4 pounds, but it is 9 units from the origin. Therefore, the moment about the origin is going to be 3 plus 2 plus 20, or not 3, excuse me, 0 plus 2 plus 24 plus 36. So that is 62. Now, in this case, the mass is just the sum of the weights, 3 plus 1 plus 4 plus 4. So the mass is going to be 12. This means that if I want to find the actual value where the center of mass is, what we call X bar, I would simply take the moment about the origin, 62, and divide that by 12. 62 divided by 12 is about 5 1/6. And what this means is if I had this scenario, if I put a fulcrum 5 1/6 units at an X value of 5 1/6 units, then everything would balance at that X value. So as a visual, imagine we have these weights on the number line, the x-axis, and the heights of these are basically the weight of each one. Whoops, excuse me, that should not be up to 5. Hold on. That should be to 4. Excuse me. Yep. So 3, 1, 4, 4. And what we're saying is that at 5 1/6, so right about where this cursor is the point of balance. All right. So if I put the fulcrum a little bit above 5, then these weights are going to balance. There's the line there of where you'd put the balancing. Again, this is assuming that this line has no weight itself, that we're just talking about these 4 weights. So we, in order to find the center of mass in this one dimension, we calculated the moment about the origin. That was basically how far along on the x-axis are we. We saw that we calculate that moment about the origin, then we divide it by the total mass, and that gives me the center of mass, the point at which we would balance. Now, this is an x value because we're talking about in one dimension. What if we are dealing with something in two dimensions? We're going to take a look at planar laminas. Planar lamina is just a fancy word for a flat piece of material, like a plate, like a sheet metal plate, with common density. So the weight of this thing is going to, if I took a 1 by 1 square over here on the left, it's going to weigh the exact same as a 1 by 1 square over here on the right. When I'm thinking about planar laminas, I often think about a piece of sheet metal or a flat piece of some other substance. So it doesn't always have to be metal. You could do a flat piece of wood of a weird shape, but it's just this flat piece of an object that's cut maybe in a weird shape, maybe not in a weird shape, but in a shape. We want to find the center of mass for the planar lamina. The center of mass is going to be the balancing point as long as we have constant density. And that's also going to be called the centroid. That's the balancing point. These two things are the same when we have this constant density planar lamina. They could be different if we changed that, if we changed density. We had variable density. So center of mass, centroid of a planar lamina is going to be the point of balance. Think about turning this sheet or turning this object horizontal and then putting your finger or putting a fulcrum at a point. Where would this thing balance? Obviously, we're talking about no outside factors influencing it, so we're not trying to balance it in a windy situation or anything like that. We're not trying to, put objects on this. We're just saying we put a fulcrum. Where do I set this sheet so that it balances on the fulcrum? Now, in a two-dimensional system, our center of mass is going to be located at a coordinate point or coordinate pair, a point which has an x value and a y value. The x value is going to be determined by a moment divided by the total mass of the object. The y value is also going to be determined by a moment divided by the mass of the object. Now, we get some weird subscripts here. Oftentimes, people get thrown off by the subscripts. The subscripts mean the moment about the y-axis. So that is telling you how far from the y-axis. And if you think about the distance from the y-axis, the distance from the y-axis gives you an x value. On the other hand, m sub x is talking about the moment from the or about the x-axis. If you think about the distance from the x-axis, that gives you a y value. So that's why the subscripts kind of go on opposites. And if you went into a three-dimensional system, then it'll say the moment from the xy plane, or the moment from the xz plane, or the moment from the yz plane. and those are giving you your points. But again, moment from the y-axis is giving you an x value. Moment from an x-axis gives you a y value. So how do we find the moment from the y-axis or the moment from the x-axis? Well, instead of having weights, I shouldn't say instead of, but instead of just doing a single calculation on the weight, what I can do is I can break my planar lamina into small rectangles. And if I'm looking for the mass, all I have to do is add up those rectangles and then multiply by my density. So if this object is a flat piece of iron that's a half an inch thick, it's going to have different weight than a half inch of styrofoam. So my mass is basically going to be the area of this multiplied times the density of the material I'm using. Now the moments, well, if I'm looking for the moment from the y-axis, then what I can do is I can multiply each of these little rectangles times the corresponding x value, and that will give me my moment from the y-axis when I sum those all up. If I'm looking for the moment from the x-axis, then what I do is I take the center of each rectangle, because that's where they're balancing, and I'm going to multiply it times essentially a y value, but again, the y value is going to be distance up. So let's look at what that tells me about the formulas that we're going to be using. If I'm looking for the mass of a plate, and that plate is bounded by two curves, f of x and g of x, then all I have to do is find the area from x equals a to x equals b, and multiply it times this letter. This letter is rho, and that just stands for the density of the plate. So the mass is just the area of the planar lamina times the density of the material we're using. Let's talk about the moment from the y-axis first. This f of x minus g of x, that's the length of the rectangle. And if I'm saying how far is that from the y-axis, well, it's whatever x value we're at. So it's the x value times the length of the rectangle. And then add those all up, take our limit going to 0, we get an integration from a to b. Then, obviously, I multiply by the density of whatever object we're dealing with. The moment about the x-axis is probably the most difficult to get. It's the f of x minus g of x. That's the length of the rectangle. And then, like I said, when we talk about how far is it from the x-axis, well, the center of that rectangle is at f plus g over 2. That's just the basically middle of that rectangle. So when you talk about how far up above the y-axis you are, well, this weight here is going to be centered in the middle of the rectangle, which is this, which is basically the y value we use, is the middle of the rectangle. And then obviously integrate from A to B, multiply times density. So imagine I have a couple of curves in space. One is some weird cubic equation, and the other is a nice linear equation. The cubic equation is above the linear equation from essentially negative infinity up to just a little over 10. So let's say I want to find the center of mass of this weird planar lamina object from x equals 0 to x equals 10. Well, I'm going to be drawing rectangles in here at different places. And then I'm going to be using those rectangles to find both the mass and the moments. So if I have a bunch of these different rectangles and lots and lots and lots of these rectangles all throughout my region, then I can just sum up these rectangles and get a good approximation for the area of my region. If I let the limit as the width of those rectangles go to 0, then that Riemann sum turns into an integral, and that integral is just giving me the area. And so if I take the area times density, then that gives me my mass. In terms of how the moment from the y-axis, well, I'm going to take into account the height of this rectangle. That's like a weight. And then I'm going to multiply times the distance from the y-axis. This rectangle has distance from the y-axis of this x value of 6. This rectangle has distance from the y-axis of the x value of 9. This should be very similar to the one-dimensional moment that we saw earlier. In fact, I'm using sort of the same tops of rectangles here. So this rectangle, as far as distance from the x-axis would be, or from the y-axis would be 0. So when I multiply each one of the heights of these rectangles, again, that's like the length here, times the x value, I'm getting, and then summing those things up, I'm getting an approximation of the moment from the y-axis. When I take the limit as the rectangles get thinner and thinner and thinner, then that becomes an integration of x times f minus g. So that's where I'm getting that formula from. If I'm talking about the moment from the x-axis, the weight of this rectangle is going to be the length of it times the density. And if I'm wondering how far up I need to go, well, the middle of this rectangle is going to give me where all of the weight of the rectangle balances. So each individual rectangle is going to balance at the middle of the rectangle. The middle of that rectangle is f plus g divided by 2. So if I take the middle of the rectangle multiplied times the length of the rectangle, and then sum up all of those, then the sum of those gives me approximation for the moment about the y-axis, letting the rectangle's widths go to 0, turns that summation into an integration, and I'm just integrating midway point of the rectangle times length of the rectangle with respect to x. Hopefully that makes sense as a visual of what I'm doing. So moments are a bunch of, again, about the x-axis, midway point of the rectangle times length of the rectangle. About the y-axis, it's length of the rectangle times how far in the x direction we go, which is just an x value. And then the mass is just the area of this object. So sum up a bunch of rectangles gives you the integration. So that's where all these formulas come from. And again, don't forget to multiply times the density of whatever object we're doing. So mass is density times this. Now it turns out that when I take the moments, I also need to multiply it times density. Moment about the x-axis, again, averaging the rectangles, or excuse me, the average of f plus g times the length of the rectangle. Moment about the y-axis is just x times the length of the rectangle. And then multiply by the density. If I'm looking for, again, the center of mass is moment about the y-axis divided by m as my x value, and moment about the x-axis divided by m is my y value. Notice that when you divide these two, the density is going to cancel out. And so it turns out whether or not I have a plate that's a constant thickness steel plate, or whether my plate is a wood plate of the exact same shape, or whether my plate is a styrofoam plate of the exact same shape, the center of mass, or the centroid of that thing, is going to balance at the same point. So let's start doing some calculations. Let's find the center of mass of the planar lamina of uniform density rho bounded by f of x equals 4 minus x squared and the x-axis. The first thing I probably want to do is take a look at this drawing. So the x-axis is the line y equals 0, and 4 minus x squared is this parabola pointing down. So when we're talking about the planar lamina bounded by these things, we're talking about the closed bounded region that these two make. And in this case, it doesn't just say in the first quadrant, so we must be talking about both the second quadrant and first quadrant sections of this. Notice that goes from x value of -2 to x value of +2. Those are going to be my bounds. And then if I were to draw some sort of a rectangle in there, that might be a little bit thick. So you draw some sort of a representative rectangle, it's going to look like this. It's going to have top, which is the f of x, bottom, which is g of x equals 0 or y equals 0. And we're, again, bound are going from -2 to 2. Oftentimes, instead of writing y of equal to 0. All right, g of x equal to 0, because that's the one on the bottom. So when I go to find the mass, well, the mass of this object is going to be whatever density. It didn't give me the density as a number. It gave me the density as just rho. The bounds are, again, from -2 to +2. And then F is going to be 4 minus x squared. G is going to be 0. And this is something I can plug into my calculator, and that will give me my mass. I think I'll erase that one and just write that in my calculator. So what we're going to get is when you integrate from -2 to 2 of 4 minus x squared with respect to x, obviously, you get about 10 and not about, you get exactly 10 and 2/3 times rho. Don't forget our density. So that's my mass there. 10 and 2/3 is the area of that object that we saw in green times the density of rho. If I want to find the moment about the y-axis or the moment about the x-axis, it doesn't matter which one I do first. I think what I'll do is I'll do the moment about the y-axis first. So I look at this formula and I say, I know my bounds for my x values go from -2 to 2. We're using x values because we're integrating with respect to x. My top function, that's the f of x, is 4 minus x squared. The bottom function, the bottom part of that region, is y equals 0. This is something I can plug into my calculator as well. If I just put second enter, oftentimes I can just insert the variable x in front of what I had last time. So in other words, I wrote this thing last time. If I just insert an x in front of that, then that changes to my moment about the y-axis. Doing that gave me 0 times rho, or just 0 for my moment about the y-axis. That means in the x direction, it should be balanced right where the y-axis is. So at, in other words, x of 0. Now my moment about the x-axis, what I would do is I would take an average. So I take 4 minus x squared plus 0. Be careful about adding or subtracting there, because a lot of people will put subtract and then subtract again, or a plus and then a plus again. Here, we're adding the two functions and then dividing by 2. Here, we're subtracting the two functions and doing nothing with those. So be careful about that. And some people, again, however you type this, some people like to, instead of dividing by 2 here, divide by 2 at the end. You can factor out a divide by 2. But when it's all said and done, we have to plug this into our calculator in some way, shape, or form. When I do that, when I plug it into my calculator, again, some way, shape, or form, plug this into your calculator, you can simplify, you can, multiply this times this. Now that I have -0 plus 0, you can ignore that. You get 17 and 1/15 times rho. So let's think about what that means in terms of the center of mass, which again is also the centroid of this figure. It's the point of balance as long as we have constant density. Okay, again, center of mass, if we have this planar lamina of constant density, then that's the point of balance. So the x value is going to be determined by the m sub y, the moment about the y-axis, divided by the mass. The y value is going to be determined by the moment about the x-axis divided by the mass. In my case, that is going to be 0 divided by 10 and 2/3 times rho. That's the x value. And the y value is going to be 17 and 1/15 times rho divided by 10 and 2/3 times rho. It's a little bit now that we have that. Obviously, I'd like to clean that up a little bit. 0 divided by anything is just 0. If I take 17 and 1/15 and divide it by 10 and 2/3, I get 1.6. And notice that again, density over density, this rho is canceling out. And so therefore, it doesn't matter if this object was made of cardboard or a steel of constant thickness, or a piece of wood of constant thickness, constant density. The center of mass is going to be at 0, 1.6. And that's how the calculations go. So the calculations go just like that. I got to find my bounds sometimes. Sometimes they'll be given to us. And then again, mass is just F minus G. Moment about the x-axis, F plus G divided by 2 times F minus G. And then the moment about the y-axis is just the x value times the quantity F minus G. Let's graph this point on what the object that we just drew and see if it makes sense. So here's the point at which this planar lamina that I have shaded in green should be balancing. That's the point 0, 1.6. And hopefully it does make sense that left and right are going to be balancing along the y-axis because those are mirror images of each other on the left-hand and right-hand side of the y-axis. Also, it should make sense that while the height of this object is 4, a little more weight is going to be at the bottom because this object is a little bit thicker at the bottom. So it's not going to balance at 2. It's going to be shifted down a little bit. And that shift down a little bit towards the bottom is because there's more stuff at the bottom, more things at the bottom. So we are balancing at the point 0, 1.6. Again, that should intuitively make sense. If I put my finger there, turn this thing horizontal, it should balance on my finger or a fulcrum or whatever. Let's do another example. Let's find the center of mass of the lamina of uniform density that is bounded by this f of x, and this g of x. F of x is equal to negative x squared plus 4x plus 2. G of x is equal to x plus 2. Now we've actually looked at this object before when we were calculating areas, so it should be fairly straightforward as far as what the object looks like. We also know how to find points of intersection, so I'm going to very quickly find those points of intersection using my calculator or using algebra or using some other graphing tool. So we'll take a look at the object. And again, the only closed bounded region is the one from x equals 0 to x equals 3. That is the region shaded in green here. So I'm trying to find the center of mass for this green shaded area. Again, as you can see, in this case, the parabola is on top, the line is on bottom, and the x values are going from 0 to 3. So now we're ready to plug in what we need into the formulas. Again, x values are going from 0 to 3. And that's going to happen on each and every integration, both my moments and also my mass. So integrations are always going from 0 to 3 in this example. Oftentimes I find it easiest to start my integration with the most complex, and then on my calculator, I'll hit second enter, and then I'll replace this f plus g over 2 with just the x. And then I'll hit second enter, and then I will just eliminate that x, and then that's my mass. So oftentimes I start with the most complicated. So that's what I'm going to do right now. My moment about the x-axis is going to be f, again, that's the one on top, negative x squared plus 4x plus 2 plus g, which is x plus 2. And sometimes I'll simplify that 4x plus 2 plus x plus 2. You can combine that if you'd like to give you a 5x plus 4 on top. That's usually easier to compute with. So we'll go 5x plus 4. And that's the simplified version of that. And then the f minus g is very similar, but we're subtracting. So we get negative x squared plus 4x plus 2 minus x plus 2. be careful when you're writing this because that x plus 2 should be obviously in parentheses. And if we combine like terms here, we get 4x minus x, that's 3x, and then 2 minus 2 becomes 0. So this one does simplify pretty nicely if I distribute and combine like terms. I get negative x squared plus 3x. Now I'm all set to integrate. So I can integrate again from 0 to 3. And then a lot of times what I do is I'll put in parentheses this negative x squared plus 5x plus 4. And then in parentheses, negative x squared plus 3x. And then divide that whole thing by 2. So divide by 2 on the outside of the parentheses. When you do that, you get about, well, you get exactly 19.8 times rho. Now, here's the deal. If we have all of this, now I can go back and essentially on my calculator hit second enter and delete this part and just put in an x. Because this negative x squared plus 3x, the f minus g, will be the same. So I can say f minus g now is negative x squared plus 3x, and then integrate. Again, you can do this all by hand as well if you want. It just is going to take quite a bit longer. So eliminate the parts f plus g over 2 and replace that with just an x. And I got an integration of 6.75 times rho. Now I can go back. If I'm doing this on my calculator, I can hit second enter and just get rid of the x. And now we have our mass. Because again, f minus g is still the same thing, minus x squared plus 3x. And if you eliminate that x from moment about the y-axis, you get the mass, the formula for mass anyways. And that's 4.5 times rho. Now I have all of the calculations that I need. So now I can go find the center of mass. Always remember, the x value is the moment about the y-axis divided by the mass. The y value is the moment about the x-axis divided by the mass. So we're getting 6.75 times rho divided by 4.5 times rho as my x value. And then my y value is 19.8 times rho divided by 6.75 times rho. Oh, not faux, rho. If I take and simplify that, 6.75 divided by 4.5 is 1.5. 19.8 divided by, oh, I mistyped this. I'm sorry. I looked up and I saw 6.5. I should have divided by the mass of 4.5. So sorry about that. I mistyped that earlier. So 19.8 rho divided by mass of 4.5 rho. Denominator should be the same. And then 19.8 rho divided by 4.5 rho gives me a 4.4. Again, that's without any rho because these densities have canceled out in both the x and y terms. So that's what we get. Again, I like the trick of starting with the most complex one. That's usually the f plus g over 2 times f minus g. And then deleting the f plus g over 2, inserting an x. Then deleting that x. And then that'll give you your mass. Sometimes that makes everything a little bit quicker to calculate, especially if you're using your calculator or some other computer device. By the way, we can always graph this and just visually see if it makes sense that that is the center of mass, left and right and up and down makes sense. 1.5 comma 4.4 is right here. And that looks to be the center. Obviously, the edge over here is a little bit closer, but it's also thicker over here and thinner over here. So it does appear to be the center, at least visually speaking, center of mass, visually speaking. If your point came out to, let's say 1.5 comma 3.4, then this doesn't really make a whole lot of sense for the center of mass. Or if it came out to like up here, then it wouldn't have made sense. Or if it came out to, there or just there, wouldn't make sense. But this one does make sense that that is your center of mass. So it's always good to check the visual on that. You can check it through just sketching it by hand or graphing it on your calculator or graphing it on some other computer like Desmos. Let's do another one. Let's take example 4. Here we have two curves, y equals x to the 2/3 power and y equals 4. We're going to find the closed bounded region that these two create and then find the center of mass of that region. Now, if we graph this, what we'll see is y equals x to the 2/3 power is this shape. We've seen that shape already. And then y equals 4 is this horizontal line. So the closed bounded region that we're looking at is the interior of this. Now I want to point out that in this shape, y equals 4 is the graph on top, and y equals x to the 2/3 is the graph on bottom. So when I'm calling something my f of x and something else my g of x, the f of x is going to be the top one and the g of x is going to be the bottom. If I flip those, then I'll get negative moments where I should have gotten positive or vice versa. And the mass will be negative or positive and when I should have gotten the reverse. But there we are. We're looking at this region here. By the way, the x value of this region goes from -8 to +8. So the x values go from -8 to +8, and we know y equals 4 is on top, y equals x to the 2/3 is on bottom during that section. By the way, we can see that this is symmetric about the y-axis, so I would bet that the moment about the y-axis is going to end up being 0. We'll confirm that though. So now that we know that, we're ready to rock. Oops, I don't know why that's different. So we're ready to go. And again, I'm going to start with the most complicated ones. I'm going to integrate from -8 to +8. My f is my top function, that's 4, plus my bottom function is going to be x to the 2/3 power. We're going to take that, and then I put that in parentheses and then divide by 2. And then over here, it's going to be 4 minus x to the 2/3 power. Again, and then I'll put that in parentheses. Make sure you have the right parentheses. Make sure you have the right integration. This one is going to take a second to integrate because we're talking about x to the 2/3 power. And oftentimes when you do that, your exact answers don't come up as exact answers because of the numerical process your calculator uses. So what you get when you actually calculate that is 73.1428 blah, blah, blah. If you were going to do that by hand, I believe that's 73 and 1/7 times rho. So we get that 73 and 1/7 times rho. Again, this might be off just a little bit on your calculator because of rounding if you're doing it via your calculator. And that's just because of how that works. But there it is. Once we've done that, then I can eliminate this very big first piece and replace that with an x and take 4 minus x to the 2/3 power as my f minus g. We're going to integrate that from -8 to +8. When we do this integration, we get 0, or 0 times rho, if you wanted to do it that way, which is what we expected. Remember, we expected the moment from the y-axis to be 0 because our shape looked symmetric about the y-axis. Our lamina did. Then all I have to do is go back and eliminate x. Four minus x to the 2/3 power, integrating from -8 to +8. By the way, these integrations, the mass integration and the moment about the x-axis, on the calculator take a while because, again, we're talking about stuff that's close to 0 raised to the 2/3 power. So that numerical process is fairly difficult on the calculator. We get 25.6 rho. Now, if we were to do it by hand, it would be exactly 25.6 times rho. On the calculator, it might give you just a little bit different. My calculator looked at and said that was 25.5 and then lots of 9s and then 7/7. Again, that's the numerical approximation on your calculator issue. All right, so now we're ready to do this. Again, 25.6 rho is my mass. So that is going to be the denominator of both the x part and the y part. The x is given to us by 0 over 25.6 times rho. The y coordinate of the center of mass is given to us by 73 and 1/7 times rho divided by 25.6 times rho. All of that can be simplified, of course. If I take 73 and 1/7 and divide it by 25.6, what I get is 2 and 6 over 7. The rows cancel out. And so that is my center of mass, 0, 2 and 6/7. Let's go ahead and graph that point and see if it makes sense. Hopefully all of this made sense. All of the integration made sense to give me my center of mass of that lamina of uniform density. And now let's go see if that looks correct. So I just graphed that point. Obviously, it's on the y-axis. That seems right. Also, if you look, it's a little bit, if I look at the lowest point of 0, 0 and the highest point of 0, 4 on the y-axis, it's a little bit closer to the higher values because this object is wider up top than it is on the bottom. So that is the center of mass, that 0, 2 and 6/7. Most times, if you can't recognize the perfect fraction, you can't recognize that 0.142857, whatever, is actually 1/7, then rounding would be fine. Just round it to as much as the calculator gives you, and you should be good to go. At least for my classes. Obviously, there are some classes that maybe want the exact answer, but usually 2.86 is good enough for my classes. You don't have to get the exact 2 and 6/7. But again, that's what it is. It is 2 and 6/7, and if you just see this as 2.86, that's okay too. Let's do another example. We're going to find the center of mass of the lamina of uniform density bounded by these three curves. Y equals -7/4 x, y equals -7, and x equals 0. So this is going to have three sides to it. All of these are lines, so it's got to be a triangle, right? So we're looking for the center of mass of this triangle, and we'll use integration to find that. When I graph these three, y equals -7/4 x is here, y equals -7 is here, and then x equals 0 is here. So this is the triangle. Notice on this triangle that the y equals -7/4 x is on top, and the y equals -7 is on bottom. So we're looking at this area here. So -7/4 x is going to be my f of x because that's on top. And y equals -7 is going to be my g of x because that is on bottom. Oh, and x values are ranging from 0 to this point of intersection, which is an x value of 4. So x values are going from 0 to 4. That's going to be my bounds. My f is going to be the line y equals negative 7/4 x. And my g is going to be the line y equals negative 7. Okay, I'm just going to dive into this. Again, the f was the negative y equals negative 7/4 x. The g was negative 7. I like to start at the more complicated ones. We're going to integrate from 0 to positive 4. And we're going to get negative 7/4 times x, excuse me, as my f plus g, which is a negative 7. In fact, instead of doing a plus a negative 7, we could just write a minus 7. That's what I'd probably do. We're going to divide that by 2, and then we're going to go negative 7/4 times x for my f minus a negative 7. When I type that in my calculator, I'd probably write a plus 7 there. So that is the moment about the x-axis. When I do that integration, I get a negative 65 and a third times rho. Again, make sure you type the rho in. By the way, that negative, that may shock you because all the other ones that we've done so far have been positive, but moments can be negative. That just means that we're going to be located underneath the x-axis. So moment about the x-axis being negative just means that the center of mass is going to be located underneath the x-axis. And that should make sense based on our drawing that we saw. This object is entirely underneath the x-axis here. So we should expect our moment about the x-axis to be negative. We need to go below here, go down. Now the moment from the y-axis we'll expect to be positive because our object is all to the right of the y-axis. So let's calculate that next. Again, I like using my calculator and second enter. I'll delete this and replace it with just the x. The f minus g is still negative 7/4 times x. I'm just going to write a plus 7 here instead of a minus negative 7. And then I'm still integrating from 0 to 4. When that happens, again, I'm plugging this into my calculator. I got an 18 and 2/3 times rho. By the way, if it's easier for you to type things into your calculator as improper fractions, a lot of times I'll use improper fractions instead of these mixed numbers. Here, again, we're integrating. So let's find our mass. Here again, we're integrating from 0 to 4. F minus g, we're already well accustomed to that. That's negative 7/4 times x minus a negative 7, which I'll write as a plus 7. All that's going to be times rho. And when I do that, I get 14 times rho. Now I'm ready to calculate my center of mass. So to get the x coordinate, I would take 18 and 2/3 times rho, divide that by 14 times rho. To get my y coordinate, I would take negative 65 and a third times rho divided by 14 times rho. All the rho's are going to cancel out, and I'll get some numerical value. So 18 and 2/3 divided by 14 gives me 1 1/3. And then when I take negative 65 and a third, be careful how you type that into your calculator, divided by 14, you should get negative 4 2/3. So this is my center of mass, 1 1/3, comma, negative 4 2/3. Or again, I'd probably ask people to round it to a couple of decimal places if I were typing this into Moodle or some other learning management system. But there we go. That's the idea there. Let's visually check that this makes sense for my center of mass. So I've graphed that point, 1 1/3, negative 4 2/3. That does appear to be the center of mass of this object. So there we go. That's the idea. Now, interestingly enough, this was the same triangle we dealt with in the fluid force section. And we calculated the fluid force if this on this triangle, if it were upright and submerged in water. Specifically, it was this third example in the fluid force section. And we oriented our rectangle set that the origin, or not the rectangle, excuse me, the triangle, so that the origin was this tip, the top of it, just the way I laid out my triangle in the example we just did to find center of mass. In that section, we calculated the fluid force being applied on this vertical plate by, since it's water, it was a weight density of 62.4. And then we were integrating from -7, that was the bottom of the triangle, up to 0, that's the top of the triangle. The depth of the water was always 3 minus whatever y value we were at if we had a representative rectangle. And then the length of that representative rectangle was always -4/7 times the y value. And we integrated that with respect to y. And we got 6697.6. This would have been in pounds if we calculated that. Well, now what we just did is we found the center of mass has a y value of -4 2/3. So think about what would happen if we took the line y equals -4 2/3 through this triangle and then rotated this triangle horizontally along that line. The depth of that would be the 3 plus an additional 4 2/3. So the depth would be 3 plus 4 2/3. And then the area of the triangle is 1/2 base times height, which is 1/2 times 4 times 7. And then weight density of the water is 62.4. So depth of the horizontal object, if I horizontally flip it at the center of mass, y value, times the area times the weight density of this water. So type that in, 62.4 multiplied times 7 2/3 multiplied times 1/2 times 4 times 7. And sure enough, we get the exact same value of 6,697.6 pounds. So this is another way to do those problems that we looked at in the fluid force without integrating. Or I should say, technically, we had to integrate to find the center of mass. But once we found the center of mass, then you could have actually done that problem another way. Just flip it on its side, flip the triangle through that line, which is, again, the center of mass from the x-axis. The x-axis was here. So center of mass, flip that triangle, and then area of the triangle times depth. Depth would have been 7 2/3 feet. Area of the triangle's 1/2 base times height, and multiply times the weight density of water. That gives you the fluid force of the pressure along that this triangle is experiencing in water. So kind of an interesting little exercise there. You don't have to do that, obviously, but again, it's just an interesting exercise. Let's do another example. Let's find the center of mass of a lamina of uniform density bounded by y equals the negative square root of the quantity 9 minus x squared and y equals 0. The negative square root of 9 minus x squared is the bottom half of a circle of radius 3 centered at the origin. Y equals 0 is the x-axis. So the region we're looking at is the bottom half of the circle of radius 3 centered at the origin. And we want to find the center of mass of this object. I'm anticipating my moment about the y-axis to be 0 because this is balanced. Along that y-axis, there's symmetry along the y-axis. And I'm also anticipating that the moment from the x-axis is going to be closer to 0 than it is to 3 because it's a little bit thicker, closer to the x-axis, and a little bit thinner, closer to x equals -3. Also, just as a note, we're anticipating the moment about the x-axis to be negative because we're anticipating the center of mass to have a negative y value. So pretty straightforward of how I'm going to type this in. The y equals 0 is the one on top. The x values, I forgot to say, the x values go from -3 to 3 because those are the bounds on my circle. So x values are going to go from -3 to 3. And then my f, since I'm looking for the one on top, is going to be the 0. And my g, that's going to be the one on bottom, is going to be the negative square root of 9 minus x squared. That's going to be a minus there. So we're going to be adding a negative, which gives you a negative square root of 9 minus x squared. Here we're going to have 0 minus a negative square root of 9 minus x squared. And I'm just going to minusing a negative gives you a positive square root. 0 plus that square root is just that square root. So that's what we end up with. We end up with negative square root of 9 minus x squared divided by 2 times the positive square root of 9 minus x squared. When I put that into my calculator, I get -18, and then I have to multiply times the row, so that's -18 row. For my moment about the y-axis, f minus g, we've already concluded, is 0 minus a negative square root. So that is just the square root of 9 minus x squared. I'm going to be integrating x times the square root of 9 minus x squared with respect to x from -3 to 3. Just like we anticipated, that comes out as 0. This is balanced along the y-axis. To calculate the mass, we're going to go from -3 to 3 once again, and then we've already established f minus g is the positive square root of 9 minus x squared. That's minus the negative square root, so you just make it a positive 9 minus x squared. And that one is the tricky one. It doesn't come out to a nice fraction. Instead, it comes out to a messy decimal. Excuse me. That decimal is about 14.13716,739. And again, we're going to be timesing it by some row density. Now, for my class, usually this is good enough because we're going to give rounded answers. If you did want to get an exact value, you'd have to utilize some tricks in terms of substitutions, some trig substitutions, and that would be fine if you wanted to. I'm not going to give a lot of time to that right now, but that's what it would be. You'd have to use some substitution stuff for that. So instead of trying to get exact values there, I'm just going to utilize the rounded version. My center of mass is going to be 0 over that 14.1. I'll just call it 137 times rho. Again, this is actually an approximate value for the center of mass. That's the x value. And then for the y value, we're going to take negative 18 times rho and divide that by the 14.137 times rho. Let me put the negative with the 18. So but that's perfectly all right. My calculator will give me, again, an approximate answer. I get 0, comma, a negative 1.27, roughly. I'll round it to 2 decimal places. And that should make sense as far as the center of mass goes. So this is the calculation. Again, this is not a nice fractional number, not a nice rational number. What we get is about negative 1.27 as far as my y value goes. Again, rows cancel each other out. Again, that should make sense that we're a little bit closer to the x-axis than we are at the bottom of this half circle. A little bit closer to the x-axis than we are the line y equals negative 3. So there you go. That's what we have there. By the way, this was also an object that we used to find fluid force on the vertical plate submerged in water. And if you do the same trick of drawing a horizontal line and then flipping this, making this object horizontal along this horizontal line where we're negative 1.27 approximately down from the origin, then the total depth is going to be about 6 plus 1.27, which is about 7.27. And then you'd multiply that times the 62.4, and then multiply that times the area of this semicircle, which is going to be 1/2 times pi times radius squared. And if you do that, you get about 6416.16, which you can go and check and see if that lines up with the answer we got in that previous section on fluid force. Again, just kind of a little interesting side note there. I'm going to do one last example here. We're going to find a center of mass of the lamina that we see here in this picture. So this is some sort of a polygon where the sides go from the origin to 0, 1, and then from 0, 1 up to 2, 3, and then from 2, 3 down to 4, 0, and then from 4, 0 back to the origin. Now, the issue with this picture, it's not an issue, but if we are drawing our rectangles for our moments about the x-axis and the moments about the y-axis, you'll notice that from x value of 0 to x value of 2, the top of this rectangle is going to be determined by one line. And from x equals 2 to x equals 4, the top of the rectangle is going to be determined by a different line. So this brings us to the case of what happens when it's not just the same line on top or the same curve on top the whole time. Now, for some of you, this may be obvious, but let me stretch this out. This line, since it goes from 0, 1 to 2, 3, this has slope of 1, and it goes through 0, 1. So that line is the line y equals 1x plus 1, right? That blue line here. Obviously, the bottom of this region is always the line y equals 0. To the left, we have the line x equals 0. The bottom, like I said, is y equals 0. And this other line, well, it's going to have slope, which goes down 3 over 2. So that last line is going to be y equals negative 3/2 times x. And then because it goes through the point 4, 0, it turns out that the intercept is going to be 0, 6. So you can do the calculations on that if you'd like. Now, it's not probably going to be a surprise for those of who remember the first section very well, where we did areas. What we're going to do to find the mass, the total mass, is create two separate integrations. One of them that goes from x value of 0 to x value of 2, and the other that goes from x value of 2 to x value of 4. Between 0 and 2, the line on top is the y equals x plus 1, and the line on bottom is y equals 0. Between 2 and 4, the line on top is negative 3/2 x plus 6, and the line on bottom is, once again, y equals 0. So from 0 to 2, the f is going to be y equals x plus 1. And from 2 to 4, the f is going to be negative 2/3 x plus 6. Now, we're not going to do that with just the mass. We're also going to do that with both moments as well. So we're going to take the moment, the total moment from the x-axis, and we're going to split that up into two pieces. One where we're integrating from 0 to 2, and one where we're integrating from 2 to 4. And then we'll do that the same way with the moment from the y-axis. I know there's a lot of stuff here, but the basic concept should be fairly obvious. We're integrating from 0 to 2, and then we're integrating from 2 to 4. I'll take the most difficult one to start out with. And again, from 0 to 2, the f is going to be the x plus 1. The g is going to be 0. So from 0 to 2, the f is x plus 1, and the g of x is 0. I'll write that nicer. And then again, the f is x plus 1, the g is 0. Again, write that a little bit nicer. From 2 to 4, the f is the negative 3 halves x plus 6. The g is 0. So we get f as negative 3 halves x plus 6. The g is 0. Let's eliminate it. And again, the f is negative 3 halves x plus 6. And the g is 0. Oh, that fit on one line now. Wow. So anyways, we get two integrations. We're going to do the exact same thing down here. F from 0 to 2 is x plus 1. G is 0. F from 2 to 4 is negative 3 halves x plus 6. The g is 0. The same thing with my mass from 0 to 2. F is x plus 1 minus a g of 0. From 2 to 4, that's negative 3 halves x plus 6, and then g of 0. So this is what we do. And in each case, we're going to add those two numbers up and give me a total mass, a total moment from the x-axis, a total moment from the y-axis. So we just calculate each one individually. I'll start with these. So for the moment about the x-axis, what I ended up with was 4 and 1/3 times rho plus 3 times rho. So I got 7 and 1/3 times rho as my final moment about the x-axis. And then I went down and calculated the moment about the y-axis. I got 4 and 2/3 times rho. For my first integration, my second integration gave me 8 times rho. When I add those together, I get 12 and 2/3 times rho. For the mass, when I did my first integration there, I got 4 times rho. My second integration gave me 3 times rho. So that's a total of 7 rho. Now, the one thing that sometimes people will screw up is they will take, to find the x value, they'll take this 4 and 2/3 and divide it by this 4 and divide this 8 by this 3. We shouldn't do that. What we should do is take the total m sub y, that is the total moment from the y-axis, and divide it by the total mass. And then to find the y value, I take the total moment from the x-axis or about the x-axis and divide it by the total mass. So be careful when you do this. What we're getting here is 12 and 2/3 times rho divided by 7 times rho, and then 7 and 1/3 times rho divided by 7 rho. We can simplify that pretty easily. 12 and 2/3 divided by 7, the rows cancel out, and what you get is 1 and 17/21 as the x value, and then 7 and 1/3 divided by 7 becomes, once again, something over 21, 1 and 1/21, 1 and 1/21. So that's what you get. You get these fractions with denominators of 21. And we can go up here and look and see if that makes sense. I don't know if that does. We'll see. I did this on my calculator, but you could have also just kind of eyeballed it based on this picture that we are given. So here's this object, and let's go ahead and graph that point. X value is 1 and 17/21. The Y value is 1 and 1/21. That looks to be the center of mass. We're not quite up to the 2. There's a little bit less stuff on the right-hand side of 2 than there is on the left-hand side of 2. So we would expect it to be shifted just a little bit under 2 in terms of x values. And then there's more stuff on the bottom than there is on the top. So obviously it would be down past halfway in terms of y values. So this does appear to be the correct center of mass, centroid, in this case. So if you put this horizontally and you put a fulcrum, a point, cone, it would balance at that point. So that is the end of this example and the end of this section. Remember, if you do have different sections of your graph that determine different f of x, then you just break up your graph into multiple pieces. Then the mass is the sum of all pieces, and you have to calculate each moment separately, sum up all of the moments, sum up all of the moments about the x-axis, all of the moments about the y-axis. And then your center of mass is just your total moments from the y-axis divided by m, that's giving you your x value. Then your total moments from the x-axis or about the x-axis divided by the mass, that gives you your y value. That's the end of this section on centers of mass.